very much, Domagoj. So, yeah, as Domagoj said, this is about the rule-based ontology-mediated queries. And I assume that a lot of people in this room, they are not familiar with ontology-mediated queries. So I will spend some time to introduce that and explain what is this notion. So an ontology-mediated query is just a triple of this form with three components. We have a data schema S. We have an ontology, which is basically a set of logical constraints that allows us to extract new knowledge from our input database, and a database query, right? And the evaluation of this ontology-mediated query over an S database, and by S database I mean database over the schema S, is basically a certain answer. So are all the tuples that can be entailed by the knowledge base consisting of the database and the ontology O? This is basically a logical theory. Are all the tuples that can be entailed by every model of this logical theory? Standard certain answers. So, and why we care about ontology-mediated queries, actually they appear naturally in several settings. For example, in ontology-based data access, the main task that we have to solve is to evaluate such kind of queries. Now here, we focus on rule-based ontology-mediated queries, which are basically queries, the queries that I just described. But now the ontology, it's a set of rules, actually tuple-generating dependencies, where phi and psi are conjunctions of atoms. So I will say this is somehow a modern or a new application of tuple-generating dependencies, which has been introduced several years ago. But it turned out that they can be used to model ontologies. And they are very convenient because we can deal with arbitrarity relations. And our query here is a conjunctive query. This is a standard setting, which is just a conjunction of atoms. And in this case, computing now the answer to such a query over an S database, it's nothing else than computing the chase. Sorry. It's nothing else than computing the chase. We have heard several interesting things about the chase yesterday. So we just compute the chase, and then we evaluate our conjunctive query over this instance, which, of course, may be infinite, right? And that's why, in its full generality, this problem is undecidable. And this led to a long line of research, which is still active, I would say, on identifying well-behaved classes of TGDs, which in turn gives rise to well-behaved classes of ontology-mediated queries. So a lot of people worked on that. They are still working on that, and they are trying to find such kind of classes of TGDs. So it's a zoo, and I can introduce now, I can start introducing classes for the next half an hour, which we don't want to do. It's not bad, yeah. Can take days, actually. Anyway, but the nice thing is all the decidable or the well-behaved fragments that we have can be classified in three main families, right, depending on the underlying properties. And I would like to focus on these families and the main members of these three families. So the first family depends on the notion of guardedness, which is inspired by the guarded fragment of first-order logic. Let me say that now I will use a simplified syntax. I will just drop the universal quantifiers and use comma for joining atoms. So a guarded TGD is basically a TGD with an atom in the left-hand side of the rule, which we call the body, right? So we have one atom in the body which contains all the variables. This is the guard. And this can be easily generalized to this language, which there we need to guard only the frontier of the rule. And what is the frontier? Are the universally quantified variables that appear also in the right-hand side of the implication, in the head. So as you can see here, X is the frontier, and we need to guard these variables. Okay. So this is the guarded family of TGDs, I will say. These are the main classes that appear in this family. And the main property why we get decidability is the tree model property. So the chase, although it's infinite, is tree-like in the sense that it has always finite tree width. And this allows us to prove decidability. The other family depends on this well-known notion of acyclicity. So we essentially require our set of TGDs to be non-recursive. And this is defined via the notion of predicate graph. These are standard notions. This is how we define non-recursive data. So we just build the dependency graph, which encodes how predicates depend to each other. And then we require this graph to be acyclic. Right? And now why we get decidability here? Obviously because the chase terminates. Right? This is the reason. And the other family is based on this funny name, right? stickiness. So what is that now? So actually with sticky rules, we can write down whatever we want, but we are not allowed to lose the joins. So whenever we join a variable, we are forced to propagate this. But of course, this is a global condition. If we just check locally that each rule satisfies this condition, then we are still undecidable. So we have to inductively check that this condition is satisfied. So here, this set of rules is sticky. We have this join variable, which is propagated. Now, the head of this rule unifies with the body, which means that an atom generated by the first rule may trigger the second rule. And I have to be sure that this symbol will be propagated during the construction of the chase instance. In this case, we lose stickiness. Why? Because this join variable is lost. So somehow the join variables should stick to the inferred atoms. And that's why we gave this funny name to this logic. So the goal here was to come up with a logic which is able to express unguarded statements without forcing the chase to be finite. Right? And we came up with this notion. And now, as you can see, we can easily express Cartesian products, which is a prime example of an unguarded rule. So for example, we can state this, which I guess we all agree is true, unless you have a counter example. So, and this is quite problematic, because if we combine this with some other simple rules that can build infinite chains of symbols and then compute the Cartesian product of these infinitely many nulls, then we come up with canonical universal models with infinite cliques in there. And the tree model property is immediately destroyed. So the chase can be infinite. We don't have the tree model property. The main property here is that backward resolution now terminates. So one can start from the query, apply resolution steps, and eventually, after finitely many steps, we can reach our database. This is essentially the main property. So these are the three main families. These are the main members of these families. One can go even further and extend this in a very uniform way. So for example, we can relax a bit the condition by considering only dangerous positions or dangerous variables. And what is a dangerous variable? It's a variable a position that can have a null during the construction of the chase, right? And in a uniform way, we can generalize these classes. So as you can see now, we get also weak acyclicity in there, which has been proposed in the data exchange setting. But one can easily use that, naturally use that to express ontologies. So why not? So these are the main families and the main languages that we consider here. So of course, these are classes of TGDs. Each such class gives rise to an ontology-mediated query language, right? Which is the ontology and the conjunctive query. Now, evaluation is by now well understood. We know a lot of things about this problem. The question now is, what about containment? So I guess we all agree that this is an important static analysis task with applications in query optimization. So I think it deserves our attention. Michael is laughing. You don't agree. So just to be sure that we're on the same page, this is the problem that I'm talking about. So we are given two ontology-mediated queries. And the question is whether Q is contained in Q prime, which means that for every input database over our data schema S, the evaluation of Q over D is contained in Q prime over D. Standard containment. Certain answers. Yeah. Certain answers of Q over D should be contained in the certain answers of Q. Or, yeah. So now, we can immediately dismiss some languages here because we immediately get undecidability. Why? Because all these weakly versions generalize data log. And what I mean by that, data log is essentially full TGDs. TGDs without an existentially quantified variable in the head. One can see data log in this way. And this can be easily embedded in these languages. And since containment for data log is undecidable, this is a classical result, there is nothing to do. Actually, our main concern was not the weakly versions, but the less expressive fragments here. So what about containment, about the ontology-mediated query languages based on these classes of TGDs? This is our main question, and this is what we want to understand in this work. So, and this is what we get. By the way, I just realized that this is the first talk which mentions a complexity class above P-space. That's interesting, no? So this is what we get. In red, we have the complexity of containment. Of the certain answers. Yeah, so I evaluate the conjunctive query over the chase, right? And I get some answer, and it's containment over this set of tuples. So in the red, we have the complexity of containment, and in parentheses, I have also the complexity of evaluation, just to get some idea how the complexity is affected there. And with these arrows, I just denote or specify in which cases we have an increase in complexity. Now, in terms of techniques, we can partition these languages into two groups, right? And I would like to sketch a bit now how we get these results. Let me start with the second group, because I think it's easier to explain and digest. So the idea here is to characterize non-containment via small witnesses. If containment doesn't hold, this can be witnessed via a small database. Not that small, but of bounded size. So this is the characterization given two queries. And let me clarify that these queries are coming from the same language, right? Acyclic or sticky. If Q is not contained in Q prime, then there exists an S database of this size. The size of the database is bounded by this, if Q is acyclic and if Q is sticky. So in case of acyclicity, we have something exponential in the number of predicates that appear in the ontology. In case of sticky, we have something exponential on the arity of the data schema. And as you can see now here, if we fix the arity, in case of sticky, what we get becomes polynomial, which is not the case in the case of acyclicity. And I would like to say that these are worst case optimal, so we have lower bounds on this. We have matching lower bounds. So this is the best that we can do. And now I guess it's easy to see, having this characterization in place, one now can devise easily guess and check algorithms. So just guess a database of this size, at most this size, and then just check whether this is a witness for non-containment. And how one can do that? By exploiting query evaluation, because as I said, we know very well how to evaluate these queries by now, right? And it turned out that this is the algorithm, and it's easy because we have this result in place. It gives, in case of sticky, optimal complexity results, because we can provide lower bounds via reductions from convenient tiling problems, which are not going to the details. Unfortunately, here we have a gap. We haven't managed to close this. We haven't tried a lot, I have to admit. But I think this is a nearly, the P to the next bit's a nearly matching lower bound. And why I'm claiming that? Because we know the following. So we know from this old paper, which studies the strong exponential hierarchy, that if we restrict a bit the oracle calls, eventually we get a class which coincides with P to the next. So if we can have only polynomially many oracle calls throughout the computation tree of the Turing machine, then what we obtain is a class which coincides with P to the next. So I will say are very close. So it's somewhere there, the complexity. Now, what about the guarded-based classes? Unfortunately, we don't have a small witness that leads to optimal complexity bounds. We tried, but we haven't managed. But what we have is a tree-like witness. So non-containment can be characterized via a tree-like database. And what I mean by that, it's a database which looks like this. This is not very useful. So this is essentially a 3D composition of our database. We heard about 3D compositions yesterday. Reinhard explained to us what is that. So what is a tree-like database? We can come up with such a decomposition where all the nodes apart from the root are guarded bags, in the sense that all the elements that appear in these bags are guarded by at least one atom in the database. So there exists one atom in the database that contains all these elements. And this is somehow corresponds to the acyclic part of the database. This is not the case for the root, but what we can show there is that the number of elements that appear in the root is bounded, right? And this is actually the bound. It's the maximum arity of the schema times the size of the query. And this corresponds to the cyclic part of the database. So whenever containment doesn't hold, it can be witnessed by a database of this shape. And now what is the good thing here? The good thing is the fact that such kind of database can be encoded as trees over a finite alphabet, which immediately makes our problem amenable to tree automata techniques. And now we can apply Michael's favorite technique number 3. So now we can devise an alternating tree automaton whose language is exactly the set of tree-like databases that witness non-containment. which immediately we get this equivalent. So if containment doesn't hold, containment doesn't hold if and only if the language of this automaton is non-empty. Now, to check that, it takes exponential time in the number of states. But since the automaton that we built has exponentially many states, which I will not explain, I guess, you can imagine, I guess, how this automaton looks like. So we get the double exponential time upper bound that we are looking for. Now, the lower bounds are easily, we didn't have to work for that. It was for free for us because it's coming from description logics. So people that are working on this, they study this problem for lightweight description logics, which can be embedded in guarded and frontier guarded TGDs, and we can get it from there. And the problem is already double exponential time hard, even for these lightweight logics with boundedity. Right, what about now frontier guarded? So recall that with guarded, we have to bound all the variables in the body. With frontier guarded, we have to guard only the frontier. So the variables that are propagated also in the head. And here what we can do, we can provide a reduction to guarded ontology-mediated queries and then just apply what we did for guarded queries. And I will not go into the details, but actually the main ingredients of this reduction are the following. I think I can summarize this in a minute. So first of all, we observe that for containment purposes, we can focus on this simpler language where the actual query is a Boolean atomic query. It's just a propositional predicate, essentially. And why is that? Because first we can observe that we can focus on Boolean queries for containment purposes. Actually, this has been already observed in this paper where they study the same problem for description logic. So the same construction works. And now one can see easily that a Boolean query, a Boolean conjunctive query, is a frontier guarded rule. Why? Because in the head we don't have any variables, which means that the frontier is empty. So there is nothing to guard. So a Boolean conjunctive query is trivially a frontier guarded rule, which now we can add in the ontology and just ask for an atomic, for a propositional predicate. So having this in place, then we can focus on this language, and then we can show that every ontology-mediated query, where the ontology is a set of frontier guarded TGDs, and the actual query is a Boolean atomic query, can be rewritten as a guarded query. Which means, and this relies on a technique known as trification. Actually, our construction is inspired by construction in this paper by Barani and friends, where they rewrite actually guarded negation fixed point sentences into guarded fixed point sentences. So our construction is inspired by their construction. And this shows that these languages are equally expressive, but only over acyclic databases. Because we know that, in general, frontier guarded queries are strictly more expressive than guarded. We know that. But if we focus on acyclic databases, then we can show that these languages are equally expressive. This is the second ingredient. And the third one is the fact that satisfiability of this language can be characterized via acyclic databases. So if there exists a database that satisfies this Boolean query, then there exists an acyclic one that satisfies the query. So these are essentially the ingredients, right? And now one can show that this trification construction here, based on trification, we can provide a reduction. So given two queries, if I trify them, right, I preserve containment. Right. So now what is trification? I didn't say anything about that. Roughly the idea is to take the bodies and try to convert them into acyclic queries, because the body is a conjunctive query, so the trification will try to convert this into acyclic queries, and from there we can go to guarded conjunctive queries, so the body will become a guarded body, roughly. But it doesn't matter if... Okay, so this is the picture, and before wrapping up, I would like to share with you a recent result, which is related to what I just discussed, which has to do with another static analysis task, which we call first-order readability, which is very close to boundedness. So what is this problem? So we are given an ontology-mediated query, and the question is whether this query now can be equivalently rewritten as a first-order query. Oh, yeah, sorry. So there is a missing author here. I'm really sorry about that. So also Carsten Lutz is a co-author of this paper. My apologies. So we are given a query, and we are asking whether this query is a first-order reliable. I think it's not a big deal. Carsten will be fine with that. Huh? I'm pretty sure. So, and what I mean by that, whether we can construct a first-order query which is equivalent to our given query. This is the question. Okay. And by extending what we did with alternating tree automata, by relying on this machinery, of course we have to extend it, and it's a non-trivial extension, but based on this machinery, one can show that this problem is decidable in triple exponential time. This is not optimal. We know that it's double exponential time complete, but to get the optimal upper bound, one has to rely on a more sophisticated automata model known as cost automata. Michael worked a lot on that. Please. Yeah, exactly, sorry. Yeah, this is frontier guarded and guarded queries. Okay, yeah, I missed that. So if we focus on frontier guarded and guarded queries, we can show that this problem is first order rewritable in this complexity by extending what we did for containment. But as I said, the optimal complexity is double exponential time complete, but there we need different techniques based on this more sophisticated automata model. Okay, so this is essentially what we did in this work. We know more or less what's going on now about complexity. If we focus on guarded-based classes, we use this tree-like witness property. For the other classes, we use the small witness property. Let me also say that we know what's going on for the non-uniform version of the problem. And by non-uniform, I mean when the two queries are coming from different languages. Because until now, I was talking about the uniform version where both queries are coming from the same language. So if we start combining languages now, we know what's going on. We understand the problem. And let me also say that all these results can be extended even if we consider UCQs, because until now, the actual query in there, it was a conjunctive query. All the results hold even if we have a UCQ there. And that's it. Thank you very much. Mm-hmm.
Is there any common connection, or this is just a coincidence?
Actually, we used. Let me think that. No, this was for first order readability. This was for no. In this result here, actually, for showing double exponential time hardness on atomic queries in some special case, we use this result for the lower bound. But now for sorry. What about upper bound? So what is the connection? Pablo, do you remember something?
It's similar, and actually all upper bounds continue to hold when the left-hand side is the data loader. So it's really the right-hand side that becomes the restrict. Not the iris, not arbitrary iris, but if it is full data loader, then the upper bounds continue to hold. Yeah, but it's a refinement of those techniques.
Yeah. Great, thank you.